All right, so we're going to use Cauchy's product rule here and apply it to this thing in red. Okay, so that's f double prime times f, right? Okay, so, and you know what, I think these indices down here can be switched, and I'm going to use them just to keep it consistent. This can be b sub j and c sub n minus j. So let's do that. Okay, following this formula here, we have the series going from 0 to infinity. And then we have series going from j to n. And f double prime is right at the top of the page here. That's the one that was going to be evaluated at j. So we have j plus 1, sorry, j plus 2, j plus 1, a sub j plus 2. And that is multiplied by, might not actually need that there. That's multiplied by f, and the f series is, just to remind you, is the original thing we started with, right? It's just going to be this. Right, and that's going to be evaluated at n minus j, those coefficients. So this is then a sub n minus j. Okay, so now we're ready to plug stuff in. We have this, so we can just plop it right in there. Maybe we can do this all in this corner of this page. I'm not sure. We can try. Okay. So plopping stuff in, we've got the series. So everything's going to have the same series n going from 0 to infinity out front. So let me just put that out front of everything. 2 times the f triple prime stuff. So 2 times n plus 3 times n plus 2 times n plus 1, a sub n plus 3. And everything's going to have eta to the n common to it. So we'll just wait and multiply that by that in the end. Oh, that reminds me. I forgot to put that in the red thing, right? And I forgot to put that in the identity too. So that should be down here in the identity. That should be an x to the n. Okay. All right, so we plugged in the f triple prime stuff. Now we're going to put in the red stuff. So that'll be plus series j going from 0 to n, j plus 2, j plus 1, a sub j plus 2, a sub n minus j. I think that's everything. And then this is all times eta to the n equals 0. Okay, cool. So the next thing you want to do is to evaluate like terms on both sides. And this is just like if you're doing like partial fractions or method of undetermined coefficients, we look for the eta to the n terms. Okay. So, all right, so the eta, so we evaluate like eta to the n terms, okay, on each side. And by the way, I should probably make some steps here. I called step A, assume this form and then take derivatives or whatever. I guess B could be put stuff in. This is step B, put stuff in. And then maybe step C could be evaluate like terms on each side. evaluate like terms on each side. So we're going to evaluate the eta to the nth power terms. And all this amounts to really is dropping the series sign and dropping the a to the n. Now, it's good to point this out. If this was a non-homogeneous differential equation, then you would evaluate things like constant terms and get something, and then evaluate other stuff, and eventually evaluate a to the n terms. But there'd be more than just dropping the series and the a to the n, if that was the case. Okay, so this, I'm going to just kind of cram it in here. This is just effectively leads to 2n plus 3, n plus 1, sorry, n plus 2, n plus 1, a to the n plus 3, plus the series, j going from 0 to n, j plus 2, j plus 1, aj plus 2, an minus j equals 0. Okay, so it leads to that, which gives you your recursion relation for the coefficients. So step D would then be, okay, I already did that. I wrote that earlier, and this is around when I found out there was actually a typo in a previous recording. I'm going to probably make a bunch of typos, but you can always contact me to talk about stuff. Okay, so let's copy down what was on the last page here. 2, n plus 3, n plus 2, n plus 1. So and this is going to be step D. We'll say solve for the highest subscripted coefficient. In this case, that's a sub n plus 3. Actually, we can just do that, right? So it's going to be a sub n plus 3. There's a plus here in terms of everything else. So a sub n plus 3. Okay, and then so the numerator is going to be negative j going from 0 to n. It's a negative sign. Make sure that's clear. J plus 2, j plus 1. Okay. aj plus 2, a minus j. Divided by 2, n plus 3, n plus 2, n plus 1. Okay. Okay, and so together, your original series guess and these two together make up your series solution to the Blasius problem, which he found a long time ago. But this is the way to go about it. And we know some things, right? So we need to know to start this recursion up and get these coefficients. We need to know 3 things. We need to know a sub 0, a sub 1, and a sub 2, right? And we know those things, right? So we know that a sub 0 is f of 0, which we know is 0. We know a sub 1 is f prime of 0, which we know is 0. And a sub 2, normally you wouldn't know, and normally you leave this as an unknown variable to be predicted later by the method I'm about to show you. But to make things simple right now, we're going to just assume that we know it. And right, a sub 2 would be, what's that? It's the second derivative evaluated at 0 over over 2. So for us, that is 0.4696 over 2. 4696 over 2, approximately, because I left off, we stopped at the 4th digit, and presumably this is a irrational number. Okay, so given those, you can get all the other coefficients. So let's see what happens with this series, and that's going to motivate the asymptotic approximant that we're going to use. I'm going to pull up MATLAB, and we'll start a code where we'll have the numerical solution, the series solution, and the approximate solution. Okay, so I'll just open up a new file here. Let's call this Laplace approximate. Like I said, I'm going to try to do everything from scratch, so you can even sort of see the approach that I'm using in the code. I always start with that. Okay, so I don't know, let's go from 0 to 10. How about eta equals 0 to 10 in increments of 0.1. Yeah, let's do that. Oh, okay. We should probably have a d eta, which will be our independent variable step. Do we want that to be our numerical step? Why not? We'll make it that for now. We don't need to, but we can. And real quickly, let's just write a little Euler's method solution of the problem. Okay, so we know the initial conditions, right? F. F at 8 equals 0 is 0, right? And df 0, and so we'll say this is the df d, this is f prime at 0. And ddf is 0.4696. Okay, so let's just solve this problem. Where's our differential equation here? There we go. Okay, so right. Okay, so we're going to define. Okay, so ddf. Okay, so ddf n plus 1 equals ddf n plus d eta times the stuff that would be on the right hand side, which would be negative df n times f of n over 2. I think. Okay, so that's just the differential equation saying the third derivative, right? If we move the ddf over the other side of n and divide by d eta, that's the third derivative equals the negative second derivative times the dependent variable itself. Okay, so then we need to just advance those two derivatives. So we're saying that the second derivative is the derivative of the first derivative, right? So df n plus 1 df n right, times ddf of n. Okay, sorry, I think about that for a second. We also want to say that the derivative itself is defined. Okay, let's just see if that runs. Okay, didn't give me an error. That's good. So this is Euler's method. Just breaking this down. Euler's method. Find first derivative. Second derivative. Differential equation itself. Okay, and then we want to plot this. So eta f, and let's use circles. Must be the same length. Okay, so next up here, this needs to be -1. Cool. That looks pretty good. I mean, I don't know if that slope is exactly 1, but it's going linear, right? So it seems to be matching the infinite condition. All right, so that's the numerical solution. Now let's put in the series solution. So A0 is equal to that. A1 is equal to that. A2 is equal to this, as we defined on the Jamboard. Okay, and then we're going to put this at the top here. We're going to specify the number of terms in the series. Oh, yeah, I should probably say some things about this. Is the numerical time step. This is your time interval, and then say let's use, I don't know, let's start with like 3 terms in the series, and this is our terms and number of terms in the power series. Number of terms in power series. Okay, so our recursion is right here. Now, this is another reason I wanted to include all these details, including the code in this recording. I just want to show you the way that I enter in the coefficients, because this is the same way I'll be entering coefficients into MATLAB, or whatever language you want to use. You might steal some of these techniques for the approximant itself later. Okay, so just going to squish this a little bit for a little while. Okay, so first I'll just start by saying, okay, so A of m plus 3, I'm just copying over what I have here circled in, equals negative. Now I'm just going to call this J sum for a while, and we'll just define J sum up above. J sum divided by 2 times n plus 3 times n plus 2 times n plus 1. Okay. Now to deal with J sum. Okay, so J sum, we'll say equals something, and then for J equaling, now here's the thing. So MATLAB does not like indexing at 0. So where's it going to be 0? It's going to be 0 when J equals n. Okay, so 0 is not a problem, but n is a problem. So going from 0 to n minus 1. And outside of it, we'll include the nth term. So this will be the nth term outside. Okay, so J sum equals J sum plus do I want to include the negative? The negative's already included, right? Okay, J plus 2 times J plus 1 times A of J plus 2 times A of n minus J. You'll see there'll never be an A of 0 the way that we have this. We're going to include the nth term up here. That's how we're going to start it out. Usually you'd make J sum at the beginning be 0, but we're going to use the nth term. So evaluating J at J equals n. So this becomes n plus 2 times n plus 1 times A of n plus 2 times, well, when J equals n, that's going to be A sub 0, right? Okay. I think that that's everything. Let me run it to make sure there's no typos. There is a typo. Okay. And next we'll see the number of array elements, and you may have already found this if you're watching it. Oh, okay. So doesn't like that. Because we have A sub 2, and this is A sub 3 right here. So that's interesting. Okay, so we want to oh, start this at 0. There we go. Cool. All right. Right, because then I'll start this out at 3 instead of 4. Now let's plot the series solution. So for n 0 from 1 to n, I guess we could use 0 if we wanted to. No, that's going outside of the thing. Okay, so f sum equals A sub 0. F equals F plus A of n times eta to the nth power. Notice I use a dot caret because we're taking the vector, or the array eta up here, and we don't want to do a matrix multiplication. The sizes won't work anyways, right? We just want to raise every single thing inside that array to the nth power. So we use dot caret instead of caret. And we want to plot the solution. So I guess we could plot it as we go here, just to see what it looks like. Eta F, we'll make these dashed lines. Hold on, and how about draw now and pause. The draw now makes sure that it automatically prints it to the screen, doesn't go to end. And this one we want to watch this go. So let's see if this works. Oh, I should actually put the hold on at the top so we keep the numerical solution on there. Oh, that's already looking pretty good. That doesn't make any sense. Oh, this should be F sum. That's why it looks good. Okay. That's weird. It's not plotting anything. Oh, it's because these are not F sums. There we go. I don't know if you can see that, but it is plotting something there. It doesn't look the greatest. Maybe I should make these black. And let's crank up this to 10 terms. I want you to show you something. And this one, it actually, for the Blasius series, it skips terms. There's 2 0 terms in between every non-zero term. Okay, so we're not going to see. Maybe I should go up to like 15 or something. So that's I think that's n equals 1 probably. That's I think it's n equals. Why don't we print it? We'll print this. Okay, so we will print to the screen what n is. So that makes n equal 1, n equals 2, 3, no change, 4, no change. That's 5. No change for 6, no change for 7, 8. Here's what we're going to do because the axis is changing, because the series is diverging. So we're going to say axis 1 is equal to axis. And here we're setting the axis by the numerical solution. Okay. And then we're going to say axis. Okay, let's try this again. 5 terms. 8 terms. 11 terms. That's 14 terms. Okay. It's not getting better. You can see that there's a radius of convergence here. And it's happening around, well, I don't know. Let's crank this up a little bit. So I'll take off the pause and crank this up. How about to 50 terms in the series? All right, so it looks like the radius of convergence is around 5, a little bit after 5, right? So the series solution is fine if you're looking between 0 and 5-ish, but then after that, it's not doing good. And there's a reason for this. The actual solution goes to something that's linear as eta goes off to infinity, and the power series solution can't do that. I mean, it's a bunch of it just doesn't have the capability of doing that. You're adding new powers in your series, and also it diverges due to singularities, which we cannot really tell where they are. Somewhere, it's not a positive singularity because there should not be any place for positive eta where this thing would blow up. Or we would see that in the numerical solution. So for either a negative eta or a complex eta, an eta in the complex plane, there's the distance away from the origin has a magnitude of around 5. And so that's causing that to diverge. Okay, so so asymptotic approximants. How do we take this series and make it so it matches the infinite behavior and gets past this radius of convergence? Okay, so to do that, so we did step 1. We got the power series solution. It's divergent. We now are going to use the piece of information that we did not use at all for the power series, and that is this condition right here. F prime of infinity equals 1, approaching that linear slope as eta gets large. Okay, and so this is the 2 pieces you need for an asymptotic approximant. It's a series solution at one end of your domain and some kind of asymptotic behavior at the other end of your domain. That could just be the leading order, like right here, or it could be a different asymptotic expansion about another point in your domain. Okay, so, all right, so let's talk about this. So if we want the solution to behave like that, there's a few different things we could do. There's a million different things we could do. Step 2. Make up an approximant. And the first approximant that you make up is not going to be the best, but you just got to try something and then work towards something that's better, that matches behavior at the other side of domain. So for the example, here we know that f prime of infinity is 1.